Hi and welcome to a lesson of multivariable calculus. And today we are going to talk about the partial derivatives. And we are familiar with the ordinary derivatives, and we know how to find the derivatives of function of single variable. Now, in this class, we will discuss how to find the derivatives of multivariable functions. So let's start with an example, that is rate of change of temperature in a metal rod. Now, since we know that if a rod is heated and we want to find the temperature T in this rod at any point, so we can say that the temperature is the function of the x direction, because heat is moving in the x direction. Let's say if we have some heat source here and heat is supplied at this end, we know that heat transfers from higher concentration to lower concentration. Therefore, the heat flows from this region towards the right. So it flows in the x direction. Therefore, the temperature is a function of x, and we can find the temperature at any point in the rod. Now, if we are concerned that what's happening with time as well, for instance, we have a rod like this, and we are concerned to find the temperature at this point, let's say at some time A, right? Sometime A, and then again, if we are interested in finding the temperature at the same point after some time B. So that is, we can see that the temperature is not a function of x only, but now it's a function of x and t as well. So as the uh, time is moving on, the temperature is changing in the rod, and as well as we are moving forward in the x direction, we can see that the temperature is changing. Therefore, the temperature is now a function of a space and time. So this way we can think of derivatives of multivariable functions. Now let's see the standard definition of the partial derivatives. So in case of single variable function, we know that the derivative of x is equals to the limit h goes to 0 function at some point x plus h minus f of x divided by h. So this is the standard definition in case of the single variable function. Now, in case of multivariable function, since we are interested in two variables, say we are having a special case of two variables in multivariable functions. So let's say we have a function of x and y. Therefore, now the change in the function is not only in one direction. Now it's the change is with respect to two variables. So therefore, now the definition is the change in the x direction, say, or with respect to the variable x. This will be equals to limit h goes to 0 f of x plus h comma y, because it's a two variable function, minus f of x comma y divided by h, right? So you can see the difference here. There we have only function of x, therefore the increment is in x direction, and there is no y direction, therefore there is no y here. But in this case we have y as well with x plus h, and then here we have function of xy. So this is the standard the way to write the derivative in case of a two variable function. And again, in y direction, the change can be written as x comma y plus h minus f of x comma y divided by h. And the notation for this fx, that is partial with respect to x, we can write it as dou f over dou x. And for fy, we can write it as dou f over dou y. So this is the standard representation of these derivatives, right? Now let's see some examples that how we calculate the partial derivatives. So there is some more explanation on these. If you want to see geometrically, what does it mean? Now see this surface, right? So this is a paraboloid. It's a paraboloid. So now if we are interested in finding the change at this point on the paraboloid, so if we are interested in finding change in x direction at this point, then we know that in case of a single variable, if we are interested in finding the change at some point, it is the slope, right? So the instantaneous rate of change that we call derivative, it is the slope. So we represent this by a tangent line on xy plane. Now since here we are concerned with more than one variable, therefore the z depends on x and y. So now if we are only interested to see the change in the x direction, then what we can do here is that consider that a plane is intersecting this paraboloid at this point. A plane that is parallel to z-axis, it is intersecting this paraboloid. So what we will get on the plane is something like this, a curve like this, right? So now if we consider this curve, take this curve on z-x plane, because we are interested find the change in x direction only, then we will have a curve of this kind, right? We can see this is the curve of this kind. Now if we are interested in finding the change at this point, then we can draw a tangent line here and like this. So again, we can see the rate of change in the x direction, right? So now this line here is tangent to this point. So this line has the slope fx at this point, right? Same as in xy, in single variable case, if we have a curve and we have a tangent line, then we say that this line has the slope f prime of x at this point, right? You can say f prime of a. So this is how we can think about the derivatives of multivariables. Similarly, if we are interested in the change in y direction, or with this partial change with respect to y, then we can think of it as just considering z y plane. So we will get a line, a curve like this if the plane intersects this paraboloid, a plane that is parallel to z-axis, and we get a line like this, right? So this is the way we can think about the rate of change in different directions when we are considering multivariables, right? Now let's take a problem, and we'll see how to differentiate the functions partially. Now say we have a function here that is this function that is function of x, y. This is equals to x squared over y plus 1. And we are interested to find fx, that is change in f with respect to x, partial change, right? Now, considering the variable that is being with respect to what we are differentiating, the other variables we will treat as constant. For instance, if we are differentiating this partially with respect to x, then the variable y here, it will be treated as a constant, just as we do in a single variable of calculus, right? Like let's say if we have a function f equals to 3x squared, say f of x, and we need to find the derivative of this. We treat this 3 as a constant and we only differentiate this function x squared, so the derivative is applied in this form. Similarly, if I want to find the partial of f with respect to x, then we can apply partial operator on both sides, and therefore we can split this function in this way that it is 1 over y plus 1 times x squared. And since this is a function of y only, so it can be treated as a constant, therefore we can move it out of the operator, and the operator is only applied to the x squared. Therefore we get 2x over y plus 1. So this is f of x of this function. Sorry, fx, not f of x, fx, that is the partial derivative with respect to x. Similarly, if we are interested in finding fy, that is partial of f with respect to y, then what we need to do is we need to consider this function of x, that is x squared, as a constant. Now, if you apply partial operator on both sides with respect to y, we have x squared over y plus 1. Then we can simply move this x squared out of the operator because this is the function of x. So it will be 1 over y plus 1. So now we have x squared times, now here we have a function in the quotient form, so we can apply the quotient rule, that is y plus 1 times the derivative of 1, that is 0, minus 1 times the derivative of y plus 1, that is 1, over y plus 1 squared. By simplification, we get negative 1 over y plus 1 squared, that is equals to negative x squared over y plus 1 squared. This is the partial of f with respect to y. So this is how we evaluate the partial derivatives of the functions. Now see some more examples. Let's say we have this function here, this function here. Now it's a function of x and y. Since if we are interested only in finding fx, that is the partial of f with respect to x, what we need to do here is that we need to apply partials on both sides. So partial with respect to x on both sides, that is e power x plus 3y times sine xy. Now since both the functions here contains x and y, so we need to be careful here while computing the derivatives. So now see here, I can write this as e power x times e power 3y. We can split this way, but sine xy will remain as it is. Now see here, this is function of y only, and we are differentiating partially with respect to x. Therefore, I can move it outside. So now the partial with respect to x is applied on these two functions here. Now, since the functions are in product form, so we can apply the product rule here. Now, applying the product rule, we will get sine xy times the derivative of e power x, that is e power x, plus now e power x times the derivative of sine xy. Now, the derivative of sine xy with respect to x, it will be, just consider this y the constant, so it will be cosine xy times the derivative of the angle. So it will be cosine xy times the derivative of angle. Since y is constant, so only left with constant. So it's y cosine xy. So it's y cosine xy. So this is the derivative of the function with respect to y. Now, similarly, if we are asked to find fx x. So what we need to do is that differentiate the function with respect to x, that is find our g over our x, then again differentiate the result that we get, right? So this is also written in this way. So fxx means we need to differentiate the function twice with respect to x. Similarly, fyy means differentiating the function twice with respect to y, and fxy means differentiating the function first with respect to x and then with respect to y, and fyx means differentiating the function first with respect to y and then with respect to x. So let's see some examples on this case also. Or okay, so we can just take an example here uh, by ourselves. Let's say we have a function that is, let's take a simple function that is e power x times sine xy. Now I'm interested in finding fxx. Okay, so I need to differentiate this function twice. So first I will find fx, that is I will apply the partial with respect to x. So I will get e power x times cos xy times y plus e power x times sine xy. Now we treated this y as a constant here, right? Now I'm again going to differentiate the function. So I have to differentiate this whole function now. So now apply the derivative on this one. So y is constant, take it outside. We will left with the e power x cosine xy minus y e power x sine xy. Plus, now we differentiate this one, so it's e power x sine xy plus y times e power x sine xy. Now we can just simplify this function and you will get this fxx, right? Similarly, if I need to find fxy, so I need to differentiate this function here, what I get here, this one, this one, with respect to y. That is, if I differentiate this with respect to y, e power x will be treated as a constant. So e power x is a constant here for this piece here, this part. And then I will have cosine xy minus xy sine xy, and plus, now e power x is constant here, so it's a constant, and the derivative of sine xy is cos xy times x, right? Because x will be treated as a constant here. So this is the way how we compute the partial derivatives, and you can practice some more examples from the exercise, and then you'll have a good grip on this topic. So that's all for the time being. Thanks for watching the lesson.